Hello students, my name is Shashank Shekhar. So today is the 5th class of this electrochemistry. So basically today I will be teaching you all about the conductance. So we have covered almost a part of the electrochemistry. So you can think of electrochemistry, this chapter has two parts. The first one we talk about mainly about the Nernst equation. So in that part, Nernst equation is the most important one and our Gibbs free energy and EMF relation. Now in today's class, I will be mainly focusing on these three things like our specific and molar conductivity and our conductance in electrolytic solution. So you know about there is flow of current in our metal. Similarly, we have flow of current in our electrolytes, and we have seen the examples also of electrolytic cell and galvanic cell, which are the subdivisions of this electrochemical cell. So they both work on the principle that electric current can flow through the electrolytic solution. So today we will see these four topics, right? So if I brief our topics for today, the first one is current due to electrolyte. So we will see how this electrolytes are responsible for in current transformation. Then we will see how is this current quantified with different parameters like conductance, specific current resistance, specific conductance, equivalent conductance. After that, we'll just put a relationship between all of these so that you can make the picture more clearer. And at last, I will be dealing with this molar conductance. Okay, so these are our today's topic. For this class, one thing is important, and you can say it should be kept in mind that the previous part has almost no relation with this electrochemistry part. Okay, so if you have known nothing about the previous topic like Nernst equation and all, so you don't have to worry. So this is completely a different part of electrochemistry, and questions are asked from here. Okay, so let us start the chapter. The first one is current due to electrolytes. So how does this electrolytes help in conducting current? For that, you should be aware about one thing, that is weak and a strong electrolyte. So you know what is weak and strong electrolyte? For those who don't know, I'm just repeating it in one line. So weak electrolytes are those which are completely ionized in water or in aqueous solution, while the strong electrolyte are those which are completely ionized in this, say, our aqueous solution. Means the weak electrolyte are not dissociated properly or in the 100%. So their dissociation occurs up to only a small amount. But the strong electrolyte, they completely dissociate, 100% dissociation take place of the strong electrolytes. So what happens after the dissociation? So after the dissociation of these electrolytes, we get cations and anions, which are negatively charged and positively charged, where cations are positively charged and anions are negatively charged. So they break down into two parts. Okay, so this is the visualization of this thing. So we have our anions, we have our cations, and this is our electrolyte. So we have put this electrolyte in water and we have done the dissociation of this electrolyte into anions and cations. Now how does this help in flow of current? So if you look at this diagram, you can see that we have two parts or two terminals. We have cathode and we have anode here. So anode is negatively charged terminal and cathode is positively charged terminal. So we know the basic nature of charge, that opposite charge attract each other and same charge repel each other. So the same thing will happen here also. So this, say our anions will move in this direction. Okay, so this is cathode, right? So this will be negatively charged. So it will move from here to here, and this our cathode to anode. And this positively charged cations will move from anode to cathode. Okay, now how does this electricity conductance work? So since there is movement of charge here, and how you will say that what will happen in this case? So after this cations move here and this anions move here, this anions will release the extra electron and it will flow in this direction. Okay, so it will flow in this direction. Since anions have a extra negative charge, so it will move towards anode and release the electron here. So this is the direction of conventional current, not the electrons. Okay, so it is mentioned here also that it is conventional current direction and it is in this direction. So electron will flow in opposite direction. So you should know this. I have taught this thing in previous class. So it is a small minute point, but you must have studied this point in physics also, that the direction of flow of electrons is opposite to the direction of flow of conventional current. Now this anions will move towards anode and it will release electron, and this electron will travel like this direction. So this is the flow of electron, and these cations will move here. They will be attracted to the negative terminal, to the negative side, and this will take up this electron which is been released by anions. Now you will be asking that why it is negative here, why it is written positive terminal here. So this positive terminal means it has a positive potential, and negative terminal means it has a negative potential. What is negative potential? Negative potential means it has a tendency to release electrons. That is called as negative potential, but it is charged positively. Did you get my point? So this is positive potential. Of course, it is having a positive potential. So, sorry, this one is having a positive potential. So it will have a negative charge, and it is having a negative potential. So it will have a positive charge. Negative potential means it has a tendency to donate electrons, and positive potential means it has a tendency to gain electrons. So in this way, we can see that we have a complete flow of electrons in this direction, and due to which we have a current whose conventional direction is this one, right? So this will be our conventional current direction. So the same thing is written here. The cations which are positively charged move toward the negatively charged electron. Okay, this is cathode, and the anion which are negatively charged move toward the positively charged electrode called the anode. And in this way, the current flows in a electrolytic solution. So this is our electrolytic solution. This is our electrode. The anion moves from here to here, releases electron. It moves in this direction, goes here, and the cation which are positively charged comes here and takes up the electron. And this is positive terminal means it has the positive potential and has a tendency to accept electron, while this is a negative terminal, so it has a negative potential and has a tendency to release electron, while it is positively charged and it is negatively charged. So this is the overall flow of current. So you should remember all these things. These things are important to remember. This is a very good thing to know concepts in a minute manner, because question solving will arouse each of this concept one time or multiple time. Right. So this is covered. Next we will see what is conductance. So you must have studied this term resistance earlier also. So it is a property of a material by virtue of which it opposes the direction or the flow of current. Okay. So this is a very direct definition to know. So what it is a type of hindrance that is offered to oppose the flow of current. Simple. So we will not go into deep. We will just consider resistance as something which is hindering the flow of current, and it is a property of that material. Now what I am doing, I am taking reciprocal of that resistance, that is 1 by R. So since this resistance is the hindrance, so this reciprocal will give you the ease which the electricity flow through a solution. So you can visualize it and you can think it is a logic. So if I am taking something, some value as a hindrance, so this both are opposite terms, hindrance and this ease. So if I am taking a value which is representing the hindrance that is offered by the material, so if we take the reverse of that value, so that would be the ease or the ease offered by the material. with which the electricity can flow through the solution. And the same goes the formula, which is G is equals to 1 by R, where G is our conductance. G is our conductance. And R is resistance. Now, I want to make it clear in the start of the lecture only. So you will now come across these symbols more and often. So you should remember the symbol of each of these. So conductance is represented by G and resistance is represented by R. So keep this in mind. Then if you talk about this unit, so this is the derived unit simply, because you know that resistance have a unit of ohm. Not this ohm. I will write it here. It is this ohm. So if G is equals to 1 by R, means G is equals to 1 by ohm, that would give us ohm inverse. And this ohm is represented by this symbol omega. So omega inverse. So this is the derived unit of conductance. If we talk about the SI unit, it is Simon. And it is denoted by S. So suppose something has a unit conductance of 4. So it will be written as 4S. 4 Simon, or it can be written as 4 ohm inverse. Now one thing I want to mention here is that 1 Simon is equals to 1 ohm inverse. So it is equal. The magnitude of both these are equal. Only we are changing the units here. So what is conductance in a nutshell? If you want to imagine it, it is the ease that is offered by that material with which the current will flow through that material. So since here we are interested in solution, so it is the ease that is offered by the solution. And two important things here are to notice. The first one is it is symbolized by the letter capital G, and it has a unit of course, the derived unit of ohm inverse or omega inverse, and the SI unit is Simon, which is denoted by S. So this is conductance. Next we'll move to specific resistance. Here, one thing I want to make clear is that this resistance is not a property of a metal. Okay, or this conductance is also not a property of metal. It is a kind of, you can say, dependent upon the dimension of that metal. But this is a specific resistance. This is a property of metal. It depends upon the nature of metal which we are dealing with. So this value of specific resistance will change accordingly with the metal. So how does it goes? So if I want to say one more thing, I would say that this specific resistance is specific to that substance. So it will not change the value, its value upon changing the dimension of that material. So suppose we take 1 gram of that material having a dimension, suppose it is a cube 111 length, breadth, height, and we take another volume which is having the same substance but different volume. Suppose it is 222, that is 2 cross 2 cross 2 length, breadth, height. So that would also have the same specific resistance. So did you get my point? I'm making the point here is that specific resistance is specific to that substance and it has no relation with their dimension. So we'll see how. So if you want to know what is specific resistance, it is directly proportional to length and area. This resistance is directly proportional to length and area. We know that. Length and area. Length and area, by which I mean length by area, means directly proportional to L and inversely proportional to A. Where L is our length of the wire and A is our cross section. Sorry for not putting the picture up here. So I want to make clear what is this cross section. So children do get confused. What is this cross section? So take a wire, right? Take a wire and suppose we cut it in this part, right? We will cut it. So if you look at it vertically, or you can say from the part where we have cut, just see it from that point of view, then you can see a circle there. So since it is a cylindrical, so its surface will be cylindrical circle, and it will have some area. And this area is only called cross-sectional area. So you should remember this is very important. Sometimes you will be asked, you will be given radius and all, and you will be asked to find the area of that. So you will simply use the formula pi r square, and upon finding the cross-sectional area, you can put it where it is needed upon finding resistance or resistivity, and you can find your required quantities. So you should remember this, that this cross-section area is of the circle that we are getting after cutting our wire, and its area, cross-sectional area, will be pi r square, where r is the radius of that circle, right? So the formula is r is directly proportional to rho L by A. So we are removing this proportionality, and we are introducing a proportionality constant which is specific to that material, and it is represented by rho. This is called a specific resistance. So rho is a constant depending upon the nature of the material. So I have told it earlier also. So it depends upon the nature of material, and it's independent of the dimension of that material. Now if I want to make a definition out of here, so very good definition would be that it is the resistance of that substance which is having a length of 1 meter and an area of cross section is 1 meter square. So if you are talking about a SI unit, then so in general, if I want to say, so it is the resistance of a material which is having a length of 1 unit and an area of cross section 1 unit square. Then in that case, the resistance will be equals to this specific resistance. Rho is equals to R. So it is quite clear. So if you put this value 1 and put this value 1. So if you put this 1 and put this 1, so you will end up getting this formula. Rho is equals to R. Therefore, what is specific resistance? Again, it is the resistance of a specimen which is having 1 meter in length, which is 1 meter in length, and 1 meter cross section area. So this unit can change accordingly. We are interested in SI unit, so I am writing the SI units here. But if it is a different unit, suppose it is centimeter, then it will be 1 centimeter, and this will be 1 centimeter square. In other word, it is the resistance of 1 meter cube of the material. It is the resistance of 1 meter cube of that material. Okay, so if you take a material that is in cube shape, right, then if you find this cube to have a volume of 1 meter cube, then its resistance will be equals to the specific resistance. Is this clear to you? Okay. So if I put it in a nutshell again, so it is the resistance that is offered by a cube which is having an area of 1 meter cube, that is 1 meter height, 1 meter length, 1 meter breadth. And if you are talking about wire or something, then it is having 1 meter length and 1 meter square cross sectional area. Then in that case, the resistance will be equal to its specific resistance. This is clear. But if we move to this solution, we do not have any wire or something like that. So we'll take the cube or cuboid. Okay, we will take that cube or cuboid. So it will be simply length, breadth, height. That's it. Now, since we have seen a reciprocal of this resistance, which was conductance, and that was represented by G and has a SI unit of Simon and a derived unit of ohm inverse. Similarly, we have a inverse of this specific resistance, and it is termed as specific conductance. It is termed as specific conductance. So the same thing is written here. The reciprocal of specific resistance, that is 1 by rho. So rho was the way this specific resistance was symbolized. So if we take the inverse of that rho, we'll get our specific conductance. So opposite of resistance is conductance, or reciprocal of that resistance is conductance. Similarly, specific resistance, reciprocal would give you specific conductance. Now, how it may be defined? It may be defined as the conductance of 1 meter cube of material. So the same definition we are applying here. Only the thing we are changing here is that we are imposing this word conductance instead of this resistance. So initially it was the resistance that is offered by 1 meter cube of a material, but now it is the conductance that is offered by 1 meter cube of that material. So it will be always 1 meter cube. So if you take suppose our this cylinder also, cylindrical wire also say, then it will be what will be the formula? It will be say pi r square h and whatever it will be. So the volume of that will be 1 meter cube. Okay, this is clear. Now it is denoted by kappa. It is not K, this is kappa. So it would be written like this, I think. Kappa, right? So it is denoted by specific conductance. This kappa is the notation of the specific conductance. So remember this again. I am saying it again. Remember the symbols. Conductance G. Then we have seen our specific resistance. It is also termed as resistivity. Okay, so this one more term I have left. So you should remember this term also. So specific resistance is also termed as resistivity. Similarly, the specific conductance is also termed as conductivity. So I'm writing it here, right here. But can we also say it as conductivity? Not specific, just conductivity. Then if you look at the formula, it is kappa is equals to 1 by rho. And we know the formula of rho. It is R L A by L. Rho is equals to R A by L. So if you take the inverse of this rho, it will be L by A multiplied by 1 by R. Or it can be written as L by A multiplied by conductance, because this 1 by R is nothing but our G. Yes. So the overall formula becomes L by A multiplied by conductance. Therefore, what will be the unit of this? It will be Simon meter square. How is it so? So what is the unit of this length? Simple. It is meter. And unit of area? It is meter square. So it will give you meter inverse. So similarly, we have this G here. So G has a unit of Simon. So overall it will have a unit of Simon per meter. This is the SI unit. This is also the SI unit of specific conductance or conductivity. So remember these names also. So specific resistance is also called as resistivity. Similarly, specific conductance is also called as conductivity. Next is our equivalence conductance. So this is a cool thing. Remember this thing. This is a cool thing because it may trouble you sometimes. So this is not something which is as easy as the earlier one. Okay, so this is written wrong. It will be lambda and capital lambda more appropriately. So we'll see this thing. So what is this specific conductance? So equivalent conductance. So we have seen a property which is specific conductance. So it is a way to quantify our current, right? Or quantify our current with respect to a material. More appropriately, we are quantifying the current with respect to a material using all these properties. But whenever we see our solution or look at our solution, if we use this term specific conductance or say our conductance, it would not be that much appropriate for that kind of solution, because it is difficult to say maintain our length and area and all of this, because we do it in different container. So to standardize that, we have used a different our different terminology, that is equivalent conductance. So if you define equivalent conductance for something, it will not change with change of the volume or something like that. So how is it so? Because what is equivalent conductance? For that you should understand this. What is equivalent conductance? So it is written here. That specific conductance, it although is a suitable property for characterizing metallic conductance, I have said it earlier, because length and area are easy to calculate. It is not good for electrolytic conductance, where the value amongst other things depend upon the concentration of that solution. So this is the point that you should put focus on, that why this equivalent conductance is introduced. Why? Because when we were dealing with this metallic conductance, it was easy to deal with help of dimensions, length and area and all. But when we move to this electrolytic conductance, we have a term that is concentration, and that will define, or you can say that will regularize the current more efficiently. So we have introduced this term which will be used often, that is equivalence conductance. So while measuring the conductance of electrolytes in solution, another quantity that is more important, it is called as equivalent conductance, and this will be used in your chapter. I'm not saying that those were not important. Question may be asked from there directly using the formula, but coming upon the application part in the electrolytic solution, you will see this equivalent conductance and one more, molar conductance, more often rather than those specific and conductance, simple conductance. So what is this equivalent conductance? So it is the conductance of all the ion that is produced by 1 gram equivalent of that electrolyte. One more time. What is this equivalent conductance? It is a conductance that is offered by the ions present in 1 gram equivalent of an electrolyte. So 1 gram equivalent means, you know it very well. For those who don't know, may refer the previous chapter, so you should know it. It is important, this 1 gram equivalent. So basically, if I tell it in a short way, it is basically the molar mass. So the amount of ions that is present in 1 molar of that substance will be your, say, equivalent, gram equivalent of that electrolyte, or gram equivalent conductance. The formula which is used to find this equivalent conductance, it is lambda is equals to K multiplied phi, or kappa times phi, where lambda is the equivalent conductance which we are dealing with it right now. Okay, and this kappa is specific conductance. Okay, this kappa is our specific conductance. We have seen it earlier. Now what is this phi? So this phi is the volume of that solution in cubic meter which contain 1 gram equivalent of that electrolyte. So what is it? So what we are interested in, we are interested in finding the conductance that is offered by 1 gram equivalent. So what we are doing, so if we divide 1 gram equivalent of that substance, kappa, by 1 gram equivalent, which is the specific conductance, or the conductance, sorry, specific conductance. Okay, so if we divide it, you will get your like this. So the equivalent will be put down and the volume will come up. So if I put it simply in words, so equivalent conductance will be equals to kappa multiplied by phi, where phi is the volume which contains 1 gram equivalent of the substance, and this volume is given in cubic meters. So this was our equivalent conductance. So remember this terminologies one by one. I am introducing them all. So these are important. This will come in this will come handy when you will study this Kohlraas law and all. So they will be needed there. And also in Ostwald dilution and all of those laws, you will be requiring this equivalent conductance each and every time. Next, this is kind of a conceptual thing. You should understand this. This is very important. So it is basically, I am trying to develop a relation between specific conductance and equivalent conductance, and your, say, one more, which will be that is conductance. So I am trying to generalize all these things, that is conductance, specific conductance, and equivalent conductance. So let us see these things. What are these? So to imagine first of all, understand this. First of all, imagine that you have a solution that is present in 1 meter cube. Okay, so we are taking our electrolyte in a cube, or suppose a cuboid which is having a volume of 1 meter cube, and the electrodes which we are using are kept apart 1 meter apart. So do you get my point? So we are taking a cube which is having a volume of 1 meter cube, or say we are taking 1 meter cube of that electrolyte simply. So we are taking the volume of that electrolyte as 1 meter cube, and we are placing it between two electrodes which are 1 meter apart. So what do we understand by this? So here we are keeping the cross section area 1 meter square, and by keeping them 1 meter apart, that is the distance between them, between those two is 1 meter, means the length is also 1 meter. So what we have done, we have put the barrier on the area as 1 meter square and the barrier on the length as 1 meter. Now what will be the result of it? So the cross sectional area will be 1 meter square, of course, from these two. Therefore the conductance of that solution will be specific conductance. It is obvious, yes. So what was specific conductance definition? It was the conductance that was due to cross-sectional area of 1 meter square and a length of 1 meter. So here the same thing is followed. So since we have a distance of 1 meter and that volume is also 1 meter cube, therefore the cross-section will be 1 meter square, and hence the conductance that will be offered by that solution will be our specific conductance. So this is our first barrier that we are putting and getting one definition. Now the second thing I will do here is that I will further suppose that we are having 1 meter cube of that solution and it has 1 gram equivalent of that electrolyte. Sorry for the mistake, it is electrolyte. Electrolyte. By this, what I mean is that, again, so we are taking an electrolyte which is having a volume of 1 meter cube, and we are placing the electrodes, dipping the electrodes in that electrolyte such that the distance between the two electrodes is 1 meter. Therefore, the cross-sectional area is 1 meter square, and hence the conductance will be equal to specific conductance. Now what I'm saying is that 1 meter cube volume of that solution is containing 1 gram equivalent of electrolyte. Okay, is this clear? So what will this indicate? Now the conductance will be equals to equivalence conductance also, because the volume is kept 1 meter cube, and that 1 meter cube is only containing our, say, this 1 gram equivalent. So if you remember the formula, then when this lambda is equals to k into phi, where phi was the volume containing 1 gram equivalent. So here 1 meter cube is containing 1 gram equivalent. So phi will be 1 and lambda will be equals to k. So the conductance will be equals to our equivalence conductance. So if I generalize all of this, it would be like this. So in this case, which we have put where we have put the barriers, that we have taken 1 meter cube of solution, placed electrodes 1 meter square apart, and that 1 meter cube of solution contain 1 gram equivalent of electrolyte, then in that case the conductance is equals to specific resistance, and that is equals to equivalent conductance, because all of these have a barrier and these were satisfied by our this 1 meter cube, 1 meter square, 1 meter and 1 gram equivalent. So this should be understood by you, I think. So it is important to understand this thing. This single page will give you an idea of each of these quantity which I have covered till now. Is this clear? Okay. So we have what we have seen till now. So if we start from the start from the beginning, we have seen formulas. So I'm basically telling you the formulas once again. The first one was resistance, and then we have conductance, and we have seen that G is equals to 1 by R. So this is conductance. Here. Then we have seen specific resistance, which was rho is equals to A by L. Then we have, this is also called, sorry, this here, yeah. Then we have specific conductance. It is also called resistivity. And this one is also called conductivity. So what was the formula? It was denoted by, first of all, kappa, and it was 1 by rho. 1 by rho, and 1 by rho will give us 1 by R, L by A. That would give us 1 by R will be G into L by A. Simple. Then we have seen equivalence conductance. So this is the important one, I think. So questions are asked from here only. Most often questions are asked from here. Here also the question asked from this points also, but this is the most important. Equivalence conductance. So it was denoted by lambda, capital lambda, and K kappa upon phi. So what was this phi? This is important. Volume containing 1 gram equivalent of that electrolyte. So that is the phi value. Then we have seen a relation at last, which says that if you have 1 meter cube of an electrolyte containing 1 gram equivalent of that electrolyte, and it was placed between two electrodes which were 1 meter apart, then in that case we have seen that kappa was equals to, or specific conductance was equals to our conductance, and it was equal to our equivalent conductance. So this are the things we have studied till now. Now we are remained with one more topic, which is our molar conductance. So molar conductance, if I put it in simple words, it is the conductance that is offered by 1 molar concentration of that substance. Okay, one more time. It is the our conductance that is offered by 1 molar or 1 mole of that electrolyte, right? So let us see it. What is this? So electrolytic is conductance is important to be discussed in terms of molar conductance, because mole is an important aspect of chemistry, and you can say a crucial part of chemistry, and it is easier to denote with the help of molar conductance rather than finding the dimension of that electrolytes, because we can easily calculate the moles and then we can calculate the molar conductance. So it is the conducting power that is offered by all the ions that is produced by 1 mole of the electrolyte, and this thing is denoted by lambda m. So equivalent conductance was denoted by lambda. So sometimes it is also denoted by the term lambda EQ, which means our equivalent conductance. Here also it is denoted by lambda m. Now consider a solution that contains C moles of an electrolyte in 1 cubic meter of the solution. So what I am saying that we are considering a solution in which 1 meter cube of that solution contain C 1 mole of that electrolyte. Sorry, C moles of that electrolyte. Clear? So the volume containing 1 mole of that electrolyte will be 1 by C. Simply, so since 1 meter cube contain C moles of electrolyte, so 1 mole will be contained in 1 by C volume. Is this clear? Right. So lambda m will be equals to conductance of 1 meter cube of that solution multiplied by volume of that solution, and it is multiplied by volume of the solution which is containing 1 meter cube of that solution. If I put the formula, it will be specific conductance, which is the volume containing 1 meter cube, and multiplied by 1 by C, where 1 by C is the concentration. C is the concentration. Sorry, C is the concentration. So the final formula will be lambda m kappa by C. Lambda m kappa by C. So its unit will be Simon per meter. Simon per meter. Kappa unit is Simon per meter, and concentration unit is mole per meter cube. So the overall unit will be Simon meter square per mole. So this is the thing about molar conductance. So from till now we have seen various ways of defining the or measuring the current or quantifying the current in an electrolytic solution. The important were equivalent conductance and molar conductance. One more point I want to make here. So if you want to know the derived unit, you can do it by yourself, very easy. Calculate it by yourself, you will get it. So one more point I want to make here is that sometimes in the later class I will define it much more. You will see that we have not, or we have like this. So what are these terms denoting? So they are denoting the conductance or the molar conductance or the equivalent conductance at infinite dilution. So what is that infinite dilution? Means we are dissolving our electrolytes in a large amount of solvent such that it approaches to infinite dilution, or that volume is very large in comparison to the volume of electrolyte which we have added. So in that case we call it as infinite dilution. So we will see this thing later on. So it is basically due to pure electrolyte, you can say. Okay, is this clear? Yes. So with this I want to end my lecture. So we have seen various parts, and in the next class we will basically focusing on our Kohlraas law and our cell constant. So what is this cell constant? We will see that thing. It is basically denoted by G star and L by A. We will see those things. Why is this cell constant defined? Why it was introduced? Then we will see the most important of all of this, which is Kohlraas law. And if time allows us, we will also move to Oswald dilution law, and then we will complete this chapter. Okay. So thank you for your time. With this, I end my lecture.